Hi everyone. In this video, we're going to talk about the gradient boosting algorithm. We're going to see how gradient boosting is a generalization of the idea of AdaBoost. And finally, we're going to talk about also about XGBoost. So in previous videos, we talked about the margins for binary classification. We also talk about how all of these loss functions, we talk about three different loss functions, we're trying to penalize the negative margins in different ways. And in particular, how the loss function for AdaBoost was an exponential loss function. Here is briefly the same slide I had before on the different loss functions, and in particular the exponential loss function for AdaBoost. So what is AdaBoost? And can we understand AdaBoost in terms of other algorithms? Can we generalize it to other loss functions? Kind of those are the questions that we're going to try to talk about today. So what is the similarities or difference between AdaBoost and the boosting algorithms that we have seen so far? So the similarities are that we are computing trees in a sequential way. So we compute one tree, we use the output of that tree to compute the next tree, we need the outputs of these two trees to compute the next tree, and so on, right? And then the final model is computed by summing or averaging or weighting different trees differently, right? So that's what is similar. What is different is that trees in AdaBoost are fitted on the same data with different weights at every iteration, and fitted trees in boosting are fitted by modifying the target variable. So what is AdaBoost? And I'm not gonna prove this part because I wanna prove other things. And it's a bit tricky to prove this, but it's written in some books and also in the original paper, in some of the original papers. But basically what is happening is that AdaBoost is minimizing the exponential loss function and is using forward stage-wise additive modeling in a similar way than we did for the mean square loss function. So if you remember, well, let's actually remind ourselves what is additive modeling and what is like forward stage-wise fitting. So additive modeling is just the fact that the solution of AdaBoost is a weighted sum of functions. Okay, so that's basically just what the additive modeling means. It's just that we are summing these trees. That we're assuming that the solution have this form, right? So what about like how so if you remember, what we wanted to do in general would be to fit this, to basically to minimize this function here, which is the average loss over the training data of the sums of trees. The issue, if you remember my previous video, is that this is a very difficult problem to solve. So the way we solve this is in stages. So we consider first like a constant function, we fit that. Then we consider what is the best tree we can add to that function, and we fit that. We keep this constant and that tree fixed, and then we try to find the next tree that fits better, and so on. So we fit one tree at a time, keeping all the previous functions or trees we have fitted constant. That's basically what stage-wise additive modeling means. So yeah, so basically that's basically what I'm talking about. So we're in a greedy way fitting each function one at a time, and previously fitted functions are not modified. So basically, gradient boosting is gonna be a generalization of AdaBoost for an arbitrary loss function. So once people realized what AdaBoost was doing, so the next question was like, can we feed other functions in a similar way? So this is kind of the pseudocode for a gradient boosting algorithm. So we're gonna initialize the algorithm with the best constant for the particular loss function that we're considering. And then we are going to compute some pseudo residuals from the sample in the training set. I'll tell you how we compute that in a couple of minutes. Then we're gonna feed a regression tree to these pseudo residuals, and we're gonna keep the regions of that regression tree. We're gonna compute constants, new predictions per region using our new loss function, and we're gonna add that tree to the previous fitted trees. And at the end, we output the sum of all the trees. So this is the pseudocode, and I'm gonna right now go into details on how we actually do this. So if you remember, like the first assumption that we have is that our function f of x, our model, is gonna be a sum of weighted base models. In this case, we can think about trees, but they don't have to be trees. Okay, in the case of actual trees, you're gonna see that I am just going to drop this constants alpha m, and we're gonna be fine. I'm gonna explain why in a little bit. So basically what we're trying to minimize, this. We have a loss function that could be any loss function, and we are trying to minimize the average loss with respect to our training data. Okay, and in our particular, because of our assumptions, this is gonna be, we're gonna have some sums of trees. So, but this expression here is very hard to optimize, as we have talked in the past, and that is when we decide that we're going to feed one tree at a time, and this is called forward stage-wise additive modeling. Okay, so let's talk about the step 0. So step 0. The step 0 will consider a constant function. So we're gonna consider f0 is gonna be a constant alpha. And how we're gonna find alpha? We're gonna find alpha such that we minimize we find the best constant for that loss function. Okay, and we have seen this before, right? So if you remember, if L is equal to MSE, mean square error, we know that alpha is the mean of the targets. If L is equal to mean absolute error, we know that alpha is the median of the target in the training data, right? So this is going to be different depending on the loss function that you're considering, okay? But we know this for different loss functions. Okay, so that's our step 0, okay? Our step 0 is alpha 0 of x is equal to our constant alpha, okay? So now let's talk about step 1. In step 1, we find, in this case, a tree. Let's talk about trees. The tree T that minimizes the following equation, and I'm gonna call this phi of t, where t is a tree, and this is gonna be equal to the sum of I equal 1 to n of L of yi comma f0 plus t of x, ti of x. Remember that f0 is we already found f0, right? So we found f0, and now we are actually trying to find t. Okay, so this optimization problem here may not have an exact solution for a arbitrary loss function. So we're gonna try to figure out some kind of numerical way to optimize on this. So let's think about, we have talked about gradient descent a lot, so I'm gonna write down what gradient descent is and see if we can get some inspiration from there. So basically, in gradient descent, what we have is that we are trying to minimize f of x, okay, with respect to x. And what do? So we start by, some starting point x0, right? And then in the first iteration, we update x by doing x0, basically. Sorry, we update x by saying x0, in the starting point minus some learning rate, and then we basically take the gradient, which I'm gonna call g1. So, and what is g1? G1 is the gradient of f in x0, okay? Then we maybe call x1 is basically x0 minus, basically the current point that we are at, and we compute the gradient again. Okay, and then we update the solution to x0 minus learning rate g1 minus learning rate g2, etc. Yeah. So if you look at it, the solution of gradient descent is something like x0 minus the learning rate sum of gm, where m equal 1 to m. Sounds interesting, right? It looks a little bit, it's a sum of things. Kind of looks like we are actually trying to find a sum of things too, but the things we're trying to find are functions. So let's actually, so this is gradient descent, right? So let's actually try to write down what are we trying to optimize. So we're trying to optimize, minimum of this phi of t with respect to t, and t is 3, right? So where this phi of t, if you remember, is just basically the the loss function, basically currently we have a constant function f0, and then we're trying to find the next 3. Okay, and it's actually, this is a little bit of a difficult problem, right? So let me try to simplify it again. Okay, so so the next question I have is that what would be, what would be the best value that the best value for t of xi such that it will minimize this function here. Okay, so let's call hi be t of xi. So I'm asking, what are the best values h upper script 1, 2, 3, hn, such that this function that we have here will be minimized. So let me try to write this down. So now what I'm saying is that I want to minimize with respect to h1, hn, this function that I call phi of h1, hn. Okay, and this is, we're trying to minimize 1 over n sum I equal 1. So n of L of yi comma f0 plus hi. Okay, notice that at this point I got rid of the 3 for a second, right? So I basically, I'm just trying to ask a different question and say, hey, I have these values h here. What would be the best values of h that would minimize this function here? And I don't know if you agree with me, but at this point, these are numbers. This h1, h2, and so on. These are numbers. So I can apply gradient descent to this. Okay, so what is the solution for this h if we were applying to gradient descent? And one way to think about this is that we are at a solution f0. It's like at x0 in gradient descent, and we're gonna try to find the next step, and we're trying to find the direction of that step. We can always put a learning rate on front of it. So, but what would be the direction? What is h? So our h, say h is our variable h1, hn. What is the best direction h that we can go to locally try to minimize this loss function here? And I claim that this h is basically the gradient of phi with respect to h1, hn. So basically, because if you look at this here, it's exactly the same problem that we have with our gradient descent. So what that means is that basically that what it means is that we can, the best value of hi would be d phi dhi, and that is 1 over n we could also just kind of get rid of this 1 over n too. dl d, this is L of y f df, and this is evaluated on y equal yi f equal f0. In general, it will be f0 of xi, but in this particular case, f0 is constant. Okay, so why is that? Well, if you're going to differentiate, evaluate this function with respect to hi, you don't just one of these functions depends on hi, just the one that basically corresponds to the point xi. Sorry, there's a minus here too. So basically the best direction that we can go in, we can ignore the 1 over n, is basically this direction here, this hi here. So okay, so we have basically for every point xi, we have the best possible hi that we could that basically would optimize this loss function here. The question now is that we need a 3t. Okay, so currently what we have is values for t in some points, in the training data, but we need t for every value x. So what we do, like one possibility is to say, well, let's try to fit a tree to the data set now xi, comma, our hi. So again, we have the kind of the best his that we care about, and now we basically, what we do is say, well, let me fit a tree to this data set here. Okay, so kind of that's what we do. We fit a regression tree to the data set, and then yeah, that is good. Then we could stay here, but we can actually do a bit better than that. So if you remember, so far what we have done is that we have computed some values of h, some target values that would minimize the kind of the loss function, but at that point we didn't have a tree, we just had values that would optimize without having a tree. How do we get a tree? Well, we basically decide that that we're going to feed a tree to those xi and these his that we computed with respect to this loss function. After we do that, if you remember t of x, we can write this as, so if you remember, a tree is some constant values beta j over some regions rj, right? So basically, again, this is equivalent to say, beta 1 for x that is in R1 and beta 2 for x that is in R2, and beta j for x that is in Rj. Sorry, it's just Rj. And then we know that R1 union R2 union Rj is all Rd, or the space that we have, and we know that Rj1 intersecting Rj2 for any j1, j2, this is empty, right? So a tree divides a space in regions, and in each region we have a constant. Okay, So we have a tree, and we have a loss function. One extra step that we can do is to say, well, why don't we rewrite these constants betas to, instead of optimizing the regression function that we optimized before, to actually optimize for our loss function. Okay, so again, we got a tree. That tree is a regression tree. It comes with some constants, it comes with some predictions, right? But we could, and we are, everything we're doing is a little bit of an approximation algorithm, right? So the question is, can we modify this prediction to do a bit better, right? So can we keep the regions R1, R2, Rj, but improve a little bit the prediction in each one of these regions? Okay, so let's try to write this problem for a second. So consider one region, the region Rj, right? So consider how do we modify beta j again. So in this region, for x in this region Rj, we want to find beta j, right? So what we want to do is to minimize with respect to beta. We want to sum over xi such that this is in Rj, okay, and we want to minimize the loss of yi, comma, f0 plus beta, right? So again, this is basically, we're trying to find the best beta in this region here, okay? And again, we probably in many cases know how to do that, right? In the case of MSE, we are basically gonna take the mean of yi minus f0, right? Over, and this would be over xi in Rj, right? For my, it would be the median and so on, right? So okay, so basically what I have described is the gradient boosting algorithm for the step one, right? So far what we have is basically we're talking about phi of t being 1 over n sum of I equal 1 to n of L yi comma f0 plus t of x. So we were trying to minimize this with respect to t, and to recap, we went through a couple of steps. In the first steps, we found the best possible HIs such that t, best possible HIs so that you will optimize this function without assuming that there was a tree. Okay, after we found those HIs, then in order to get a tree, we feed the dataset xi, hi to get a tree, right? So this is our dataset, and we get a tree, okay? And then after that, after I got my tree, I take each individual region and I try to find the best constant for that region, okay? So that's a summary of the first step. The other steps are the same, basically. Because instead of having f0, what I'm gonna have is, I'm gonna have I'm gonna have fm minus 1 is gonna be f0 plus f1 of x, plus t1 of x plus t2 of x plus tm minus 2 of x, right? So that's fm minus 1. So at step m, the function that I want to optimize, phi of t, is going to be 1 over n sum of I equal 1 to n of L of yi, comma, fm minus 1 in xi, okay? And then I want to find the new 3. So this is kind of very, very similar to what we did before, except that instead of f0, I have fm minus 1 that depends on that point that we are in, okay? So it's an I here, okay? So let me show you the algorithm in general, okay? So after we have gone through the derivation, let me show you the algorithm here. So as we talked about before, the first thing we do is that we find the best constants that optimize the loss function, okay? So that is that step in here, okay? After that, we compute what we call the pseudo residuals, that in this case I call Ri. Notice that this is the same formula that we had before, but generalized to Fm. After that, we feed a regression tree to targets Ri, and then we go and compute the best constants for that particular region. We update considering the new tree that we have that we have constructed, and at the end we return the sum of all the trees. Okay, so this is a gradient boosting algorithm, and you can use this algorithm for an arbitrary loss function. Okay, so as we have seen before, gradient boosting is generalization of AdaBoost. Is fitting an additive model using stage-wise additive modeling. It can be applied to any loss function. Usually the way we actually use boosting is that we actually also have learning rates. So instead of fitting every 3, we fit every 3, but we multiply that 3 by a small constant. It's called the shrinkage. So the number of trees and the shrinkage are related. So if you decrease the learning rate, you need to increase the number of trees. One way in which you can go about optimizing this process is, for example, you fix a learning rate, let's say 0.1, and then you can find the optimal m just by trying different values of m, and then you can divide the learning rate, say, by 2, and in the same way you will multiply m by 2. So this isn't a heuristic, but it seems to work well. This is just kind of one of the most important parameters to make gradient boosting work. So this combination of the learning rate and the number of trees. So there are a few gradient boosting libraries, one of XGBoost, another one is called LightGBM, there's another one called CatBoost. XGBoost has a bunch of different parameters that I will like you guys to explore at some point. So the learning rate, the number of trees, then you can define the max depth of a tree, and here are some of the values that you could use. You can subsample the training data. Instead of just using all the training data, you can subsample it and use, say, 50% of the data to fit each tree. You can also take a fraction of the columns instead of just like all the columns. and you can define some other parameters like the minimum number of minimum weight that you need for a child tree. So you can look up this more in the documentation. With XGBoost, you can also do L1 and L2 regularization. Yeah. So finally, I wanted to talk about a little bit of a comparison between random forest and gradient boosting. Random forest and gradient boosting are both very robust algorithms. Gradient boosting sometimes perform better than random forest. Gradient boosting have more hyperparameters to tune than random forest, so random forest is almost like tuning free. Sometimes in random forest you want to control a little bit of, for example, the maximum number of features. Maybe you can control that, but otherwise it's very easy. The number of trees, the more the better somehow. But in gradient boosting you have to be more careful with the hyperparameter tuning. As we talk about, random forest uses fully grown decision trees that have low bias and high variance. As the number of trees increases, the variance of the model is going to decrease. So the algorithm cannot reduce bias, so the trees have to be deep enough so that you have low bias. On the other hand, gradient boosting uses shallow decision trees that have a high bias. And because you're going to keep feeding trees on top of what the kind of the previous tree did, you are going to reduce bias as the number of tree increases, and variance is decreased by averaging. Finally, I wanted to talk about comparison between neural network and gradient boosting. So random forest and gradient boosting models work very well on tabular data. So yeah, and so far they work really well on tabular data. They are the best models in general for tabular data. Neural networks are useful when are applied to basically raw or sensory data, speech, images, NLP. Places when the individual features contain very little information, but and you want to try to figure out want to learn more complicated features. There are some success with neural networks when you have a lot of categorical variables and when you can learn embeddings of those categorical variables. And when that is important, sometimes neural networks do well on categorical data. Here are some of the references, and thank you for listening.